All right. It's just a couple minutes after the hour here now, so had lots of time for everybody to get online and catch up. So once again, good afternoon or good morning, wherever you happen to be. This is Stephen Butters. I'm one of the product managers here at Fujifilm VisualSonics in Toronto. And welcome everyone to our webinar for today. Today we're going to be talking about the Vevo F2 imaging system, a brand new imaging system platform that we're getting ready to debut. And it is going to be breaking some pretty amazing new ground. As the title says, it's really a new frontier in ultrasound research. And our presenter today will be Andrew Needles, who is our Director of Marketing and Product Manager, as well as our Site General Manager of the Toronto office. Before we get going, just some notes about the webinar. The webinar is being recorded. We are recording live right now. We will be sending out a recording of the webinar to everyone that is registered afterwards. And also the saved file will be posted on our customer resource portal at visualsonics.com. In the webinar section, you'll be able to access that later on for viewing. All of the phone lines are muted and will stay so for the duration of the webinar. If you do have questions as we're going through, there is a Q&A button. You'll see that on the Zoom webinar interface. So please just go ahead and use that to submit questions. We will go through the presentation, which we expect to be maybe 30 minutes, 35 minutes or so, and then we'll have a question and answer period afterwards. So, please go ahead, submit those questions as we go, and we'll be monitoring those, and we'll do our best to try to get to them once we get to the end. So just a little bit about our presenter today. Andrew Needles has been with VisualSonics since 2007, and he's held many roles through that time, starting in engineering and working in product development, marketing, and as I mentioned off the top, is now our Director of Marketing and Product Management in a managerial role. And so with that, I will pass the audio over to Andrew, and we'll dive into this presentation and hear about this exciting new imaging system platform we've been developing. Go ahead, Andrew.
Well, thank you, Stephen, for that introduction, and welcome to everybody. I just wanted to first take a moment to thank everybody for taking the time today. I know it's a very challenging time out there and really unprecedented in terms of what we're going through. Everybody is most likely working remotely. You can see I'm here in my home office. I am still working on my webcam setup, so if it's a little dark, I apologize. But these are very interesting times, and I just again wanted to acknowledge and thank everyone for taking the time. We did think about this webinar as we were approaching it, and with everything going on. We did consider, is it really, the timing of this something that is right at this point? But we thought, let's keep going. Let's show what we have to offer. Our new product that is coming out later in the spring of this year, and we'll go from there. So I think this is a very apt point as we talked about the purpose and vision that we all focus on at VisualSonics. And it really is through bold innovation, the empowerment of those that are dedicated to advancement of human health. And I can't think of a more important time to be thinking about our vision this way. Obviously, we have some very small part on a research, from a research point of view in the products that we offer. But we do see the technology playing a role ultimately in trying to help cure and solve issues of human health. So the Vevo F2 platform is really the next step in our evolution as a company in driving those future translational research needs, trying to meet you, our customers, the needs that you have. And what I want to take you through today is really just an overview of what this new technology is all about, and give you a bit of a sneak peek as to what's coming. When we think about the research segments that we operate in today, our main product lines that some of you may be familiar with are the Vevo 3100 and Vevo LaserX. This is really focused on preclinical ultrasound and photoacoustics. These are the products that sit in different research laboratories, in drug development laboratories, really looking at basic scientific questions and trying to answer and model human disease. More recently, we did launch a clinical version of this product that can do, it's called the Vevo MD, and it's really used in very specialized clinical applications, in clinical research applications, looking at very small structures in the human body. And what we want to talk about today is really a new direction, which is a product, the Vevo F2, which is really aimed to serve the engineers, the physicists, the acoustics specialists that are really focused on the principles of ultrasound itself and photoacoustics, and really the ones that are pushing the limits of what the technology can do, developing new imaging modes, methods of imaging and analysis. And that's really where the Vevo F2 sits within the larger research segments that we operate in today. So I just wanted to help everyone understand where we see this product sitting relative to the other products that we do currently offer. So some of the essential specifications and things you need to know about this new platform. It is in many ways a similar form factor to our existing products. This is a design that we know works quite well. We can offer some shared parts, which makes things easier from a production and service point of view. But the main takeaway here on this slide is that all of the internals, all of the electronics developed are completely different, and I'll tell you a little bit more about that. The other big piece is what we call the triple transducer connector. This is something that on our high frequency systems in the past, we have never been able to offer. There's some real technical challenges with trying to match, do electronics and matching of cables at these high frequencies. That's something we've worked through and now are able to provide 3 active ports on this triple transducer connector that can connect a variety of different transducers. So a software interface that is based off of our Vevo 3100 technology, and the system itself is able to support the VisualSonics 256 element linear arrays and some new technologies that are being developed, the phased arrays, high frequency phased arrays, and a dual frequency array. And this is something that is in development, but I wanted you to be aware of that is part of our roadmap as we go forward. Another really key point is that our parent company, SonoSite, develops lower frequency or more conventional frequency ultrasound systems, the export system. Our new Vevo F2 system will support those low frequency SonoSite transducers. So just a little bit more about the triple transducer connector. There's vastly improved ergonomics and workflow. These ports can be connected with up to 3 transducers. The system itself can then switch through software which port is active and which transducer is active. And these transducers support a variety, connectors support a variety of transducers, and I'll tell you a little bit more about those in a second. There's a variety of different external connectors, as you can see, supporting primarily the physiological input for the small animal work that people may want to do with this instrument. For this particular customer segment, the triggering in and out is a really important piece of technology that allows you to interface with external devices or other instrumentation, and has the variety of the standard data and video connections. As far as the modes, the imaging modes, we support B mode and photoacoustics mode. This is, and all the other associated options that go along with photoacoustics, and our standard RF mode that we offer today. This is access to the RF data. And we'll talk a lot more about RF data on this new platform. One point here is the RF is fully sampled at Nyquist, and this is the next point I really want to stress. This is one of the key advantages and one of the big developments of this new platform is the ability to support frequencies all the way from 1 megahertz up to 71 megahertz. So this is truly a low to high frequency system, and it really enables complete imaging, the complete spectrum of animal models. The other primary point that I really want to stress here, then we'll talk more about this in detail, is the fact that this new Vevo F2 platform allows for access to the individual channel data and has a variety of advanced graphical system configuration tools to allow you to configure the system to then collect that data. This is what we call the Vevo Advanced Data Acquisition Mode, or VADA. And it really, again, caters to the ultrasound acoustics research and biomedical engineers who are trying to collect this very low-level data off of the platform. I'll quickly talk a little bit about photoacoustics. You can see our Vevo laser cart here. This is next to the Vevo F2. This can be coupled to the system to perform photoacoustic imaging. This is what we call the LaserX solution. So it's a combination of laser and laser and ultrasound technologies. For anyone who's familiar, and I apologize, I won't go into all the details here about photoacoustics, but if there are questions that we could certainly discuss that towards the end or later on and follow up on that. But this is a mode that we call the LaserX photoacoustic software. There's a number of different modes that can be added. A mode for doing oxygen saturation calculations, so oxyhemo, the ability to do multiplexing, spectro multi-wavelength. So this laser allows for a wide range of wavelengths from approximately 700 up to 2000 nanometers for doing photoacoustic imaging. It also supports all of the transducers, jackets, and fibers that are specific to this. I guess one of the big new advancements here is the ability to do photoacoustic imaging now at low frequencies. So there is a 5 to 10 megahertz transducer, the L38XP, which can be used in this case to do photoacoustic imaging. So a little bit more about the transducers. Here's a list of all of the VisualSonics developed transducers. You can see the frequencies range from at the low end 10 megahertz up to the high end at 71 megahertz. So these are ranges. We can see the various models that we will support on this new platform. Also important is the fact that the SonoSite export transducers can also be used with the Vevo F2. For the initial release, we'll be supporting 2 different transducers. One is a phased array, the P10XP, and the linear array, the L38XP. We envision that as we move forward after the launch of this product, that there will be additional SonoSite transducers that can be added. In principle, any export system transducer from SonoSite could be supported on this new Vevo F2 platform once we put in the time to develop all of the optimization and get those transducers up and running. So that's something that is part of our roadmap. We do envision more VisualSonics transducers being available. This will be somewhat dependent on market feedback and different animal models or different applications, perhaps even more ex vivo type applications or in vitro applications that people are trying to perform. We would look at developing more transducers for those purposes. I just wanted to give you a sense of how the images actually look on the system. This is a somewhat older image that we had done throughout the development phase, but I think it serves the point here, which is to show you, this is what we call a high frequency phantom that has a variety of small voids or almost cyst-like voids that are built into the phantom. You can see these tiny little dots if I just use my cursor here. So these are little voids. This is done with the L38. So again, we're in the frequency range. We're running around 8 megahertz. It's got a bandwidth from about 5 to 10 megahertz. And you can see that we can start to detect some of these small voids. But as we get deeper and more out of the elevation focus, the beam of this transducer is quite wide, and the resolution not being as high, we start to lose the ability to detect those small anechoic spheres. As we start moving up in frequency now, you see what happens as we go from 15 to 30. So we've got a center here around 21 megahertz, and you start to see these smaller, these spheres are on the order of a few millimeters in diameter. You start to see with much more clarity and better contrast resolution these small spheres. And finally, if we go all the way up, here we've got these very small spheres that are showing up quite large. These are now doing this at 70 megahertz. And if we put this all together, you get a sense of the scale of what we're looking at from these very, very tiny spheres that aren't even visible in the near field with the lower frequency transducers, to the ability to see them. They actually look quite large, relatively speaking, up at 71 megahertz, but in fact, these are very, very small structures. So these are all to scale. I just wanted to give you a sense of really the power of the system to be able to go from low to high frequencies. Those are the phantom images. We do have the ability to image in vivo animal models with high image quality, as we've had on many of our platforms in the past. This is looking at a mouse kidney and the adrenal gland. This is using the UHF-57 transducer. And then as we go forward, here's another image of the kidney. I hope these movies everyone's able to see these movies playing. So you can see here, we're down to about 13 millimeters in this case. So this would be a center frequency somewhere around 40 megahertz with an upper bandwidth up to 57 megahertz. So this would be a pretty standard transducer for imaging mouse anatomy. And finally, looking again, this is using, again, that same transducer, looking at a mouse carotid. You can see how tiny that mouse carotid is. Here, these are just approximately 1 millimeter intervals. You can see this carotid is approximately half a millimeter or 500 microns in diameter. So I just wanted to give you an appreciation for the types of images the system can acquire. And I want to stress the point that this platform is a high-end, high quality imaging system. We get the image quality that everyone expects from a VisualSonics platform that we've had on many of our technologies over the generations of products that we've supported. But the big shift now is to be able to do all of that high quality imaging with what I'm about to show you next, which is the Vevo Advanced data acquisition. So what we are doing here is really pairing together high image quality with access to very, very low level data. And I'm going to take you through how that low level data is acquired using the data interface. If you think of the transmit signal chain on our system, what I'm going to show, and I'll show you some screen captures in a moment, but this is the Vevo F2 user interface. We have the ability to now to configure all of the transmit and receive configuration. This is really the pulse sequence properties that allow us to set up the sequence of transmit events. We then have the ability to control the transmit pulsar itself. This allows us to configure and shape the timing of the ultrasound pulse on a given channel. We also have the ability to set the voltage rail associated with that pulsar. These are things that can all be done on the platform through a graphical user interface we will show you some of the captures of that shortly. From there, pardon me, we have the ability to then set up all of our transmit delays across our transmit beamformer. The timing of individual channels can be set. This allows for the ability to generate focus beams or plane waves or delay patterns of arbitrary shape. Finally, all of this goes into the transducer, into the imaging subject, and then back. So this is where things get interesting on the receive side. Once that those receive channels come back, we have our receive front end and analog to digital converters. This is where our new ability to acquire individual raw channel data. This is the so-called VADA point in the signal chain. This allows for offline beamforming approaches to be applied and tested on all of those individual channels. From there, we continue through our signal path with many of the features of any standard ultrasound system, the ability to do standard beamforming. We do still support the beamformed RF, as we always have on our previously launched systems. So again, if you're not interested in necessarily the individual channels, but you want information about phase and frequency information without having to do all the beamforming yourself, you can certainly still collect this RF data. We have then envelope detection, the ability to collect raw data, and finally the scan conversion, which is that going to the screen, those images that I just showed you. So again, if I can sort of put this all together, this whole system is really based around having access to these various points along this both transmit and receive signal path, and ultimately at the endpoint, having that very high quality image, which you expect and need and require, especially for some of these small animal models that are being imaged. Here's the user interface. So I've shown you sort of the schematic version of it. This is what, pardon me, this is what the system actually looks like. And the screen, the control panel, so you can see the control panel here. And now we've got all of this, these different controls. If this was live, you would see this was actually a touchscreen that has controls that can be dragged and dropped and moved around. If we go into, I'll just back up here. If I do go and I hit this button, this VADA interface, it's going to take me into an interface now that looks like this. This is our graphical user interface that allows for the configuration of all of the various parameters that I was just showing you in the transmit and receive schematic. So on our transmit side, we have the ability to set up those delay patterns. You can see here we're looking at a 5-degree angled plane wave. Again, this is just a screenshot, but you can then go in and start to select a variety of different transmit delay patterns. You then have the ability to set up the actual waveforms. Here we're looking at a 2-cycle waveform. You can set all sorts of things related to the clocks, the voltage rails. You can invert your pulses. There's quite a lot of flexibility here. You can see other built-in examples like chirps. You also have then the ability to create arbitrary user waveforms as well. That can all be done right through this interface. Once you've got your waveforms and your delays set up, you can then start generating sequences. Here's just a very simple single line. We can see we start and end. We have a single line and we're going to loop on that over and over. But we can start to set up things like a series of plane waves, for example, where we fired at different angles, say 5 different angles, and we wanted to loop on that 100 different times. Or you might want to do 5 images at one angle and then moving through as you repeat. So there's a lot of flexibility here again to drag and drop and program how that sequence looks like. Finally, then you do get a preview, and here we're looking at one individual element, element 16, gives you an RF readout of that particular element. You can also then select this button if you wanted to see them all at once, and you can start to look and see where your transmit and receive apertures are set up. So this is really nice for not only for programming the sequences, also for debugging the sequences that you've created, maybe down the road once you come back to them. And also we found it as a teaching tool, it's quite nice for people who are learning about ultrasound physics and ultrasound research. This is a nice way of understanding how beamforming schemes and algorithms are set up. So this is how the system is configured. You would then go back into the main interface, hit go, and all of that data would be the active, so you can see we would set this as the active sequence, and we would then do that data capture. Another nice thing is that for any of you who are more used to actual programming and coding line by line, all of this interface is supported and underpinned by an XML-based configuration scripting language. So if you do require the ability to get in and program things, say at a much finer level, say you've got very specific sequences across individual elements, and you want to get in and do that here, you do have that ability. Conversely, if you have a script like this, which can be exported and shared with others, you could then, if I back up, you could load it back up into this interface and take a look at what had been programmed. So not to fear if, again, if graphical user interface is too high level for you and you want something a little lower level, you do have access to this scripting language as well. So just to summarize our Vevo advanced data acquisition, it's an advanced set of graphical tools that enable custom configuration of waveforms, pulse sequences, delay profiles on our transmit. That's really what it is at this point. We do have a number of possible future developments that we do foresee coming through with this new interface. Things like the ability to have a programming interface or more of an API where you could actually program things on the system, not just really configure things. That's something that we're considering for future development. Also the ability to do more image processing, more beamforming, that environment right on the platform itself. So these are all things that we envision. This is really our first step into this area where we do want to support the biomedical engineering researchers who are interested in having, as I said before, not only really, really good image quality, but also the ability to get this very, very low level data. So just to wrap up, and I think then we'll have lots of good time, hopefully, for some questions and another discussion. Just to summarize, it's a completely new hardware platform. This is not something that VisualSonics has ever developed before, this type of technology. There's a lot of new innovation that's gone into the electronics, the transducers, and really the ability to bridge the high to low frequencies system. The architecture, as I mentioned, it does enable access to channel data, supporting all of those ultrasound and acoustics research needs. The GUI that I just showed you, or the graphical user interface, it provides a user-friendly control to configure the system. So that, and as I showed you, that graphical user interface is underpinned by an XML environment that can be used for advanced customization. I mentioned it before, but I can't stress it enough, just how this system does support this very wide range of 1 to 71 megahertz. We believe this is the first ever ultrasound system to run both high and low frequencies in this range. And as you saw, the lower frequency transducers are developed in partnership with our parent company, FUJIFILM, SonoSite. And not to be forgotten, there is the photoacoustics solution, the LaserX solution, the photoacoustics capability. This enables the full range of all of our current photoacoustic imaging capability. We think this is really important in this space as well, where photoacoustics itself is undergoing so much innovation, and we really wanted it to be part of this new offering that we are coming forward with. So with that, I will stop. I appreciate the attention. I think there's probably a few questions coming through, and I think we've got lots of time to chat about some of those things. So I'll pass things back over to you, Stephen.
Great, thank you, Andrew. That's a great overview. It's a very exciting time to see this platform being developed. And we do have a few questions that have come in. One of the early questions that came in was just in regards to how the F2 is really sort of targeted towards the biomedical engineering acoustic research community. If what we have available now, or what we are planning on having available in terms of specifications that can be shared and documentation about the system capabilities, and perhaps even programming to work with the XML in the GUI, Nevada GUI.
Right. So I think the short answer is yes. It certainly could look at providing some of that information. I think the goal of today was really to show people at a high level what the system is all about. We do hope to follow up with those that have questions and are interested in really developing some of that knowledge and expertise ahead of time as they potentially look at funding or other opportunities to have the system in their lab. So that's definitely something we could do both, I would say, through follow-up online sessions where we do more of we could even demo some of the software tools at a deeper level. And then certainly if there's other information or things that can be shared, we can certainly look at providing that type of information.
Mm-hmm. Great, good. There was one question and then sort of another question that kind of alludes to it. I think if you could speak a little bit to, you mentioned specifically the triggering, the trig in and trig out BNCs. If you could speak a little bit more to how that could be used in conjunction with VADA for external devices.
Mm-hmm. So I think one particular example that comes to mind is the ability to trigger, say, a secondary transducer system that may be something more for therapeutic use, or something where you're perhaps trying to generate shear waves or through push pulses, or if you had trying to open, say, the blood-brain barrier or do other drug delivery type applications. That's the kind of thing that we had in mind when we developed that triggering interface. You could also have the ability to trigger the Vevo F2 from an external device. So it goes both ways. That can all be set up through the VADA interface. You can set the timing intervals that you want to either trigger at or the system to be triggered. But that's the goal, is really to have it operating with a secondary instrument that may be doing some. I'm using the example of a lower frequency potentially ultrasound transducer that's doing more of a therapeutic type transducer.
Mm-hmm. Great. Yeah, there have been a couple of questions just about sort of external devices, not only transducers, but other types of external devices. So yeah, there's definitely a lot of flexibility there. One thing actually that's a question that, and it's actually something that we do have planned and is on the way, is a GUI version of this on a workstation. Where somebody could develop their own sequences, and so that they're not stuck on the system.
Mm-hmm. Yeah, I think that's definitely something we should, that's something we should be thinking about, and I think it's definitely something we would consider in the future.
Mm-hmm. Yeah. There's a question here about SonoSite transducers, about specifically which SonoSite transducers are compatible with the system in regards to the connector or the transducer types.
Right. So the connector types are the same. They were developed specifically with that in mind. So as I mentioned on one of the slides, we support two of their models today. One is a phased array. A lower frequency phased array, I believe it was in sort of the 8 to 10 megahertz range, and then the L38, which is a lower frequency linear array transducer. That was just, those are the ones we picked to start. In principle, we could try to make any of those. So if you go to the SonoSite website, you'll see they've got a whole host of transducers that are under their export system. Any of those transducers in principle could be connected to the Vevo F2. It's really just the development time on our side to optimize our software and our imaging settings to really get the image quality where we need it. So that's the work that we would do. So as we start hearing about other requests for perhaps different frequencies, different animal models, and the transducers that may be appropriate, we would want to look at bringing up some of those export transducers as well to be running the Vevo F2.
Yeah, and I'll actually add myself just a little bit further to that. It is specifically the export transducers that will that have the shared connector. SonoSite,
Right.
If you look at their product portfolio, they do have quite a number of different point of care and other systems, and the connectors look kind of similar, but they actually are different. So in the case of this F2 system, it is very specifically the export transducers that have the shared connector and have the ability to be attached to the system.
Thanks, Stephen.
Yeah, no worries. We've got some great questions here. There's a question here specifically about photoacoustics and the LaserX solution, about transducers, about which transducers would be compatible with the LaserX solution.
Right. So again, all of the transducers, VisualSonics transducers that were listed, those are the transducers. So I think there's pardon me, 5 different transducers, different frequency ranges. Also then the SonoSite low frequency transducer, the L38, will have the ability to put on those. There's an external jacket that goes on here. I'll bring my hands up. An external jacket that clips on the outside of the transducer with the light fibers, and then allows for photoacoustics imaging. If you're interested in seeing how that works, if you look at our Vevo LaserX product that's on our website today, you'll see those jackets. It's the same concept. So the idea is that you've got your ultrasound transducer, their standard ultrasound transducer, and then the addition of those fiber jackets that allow for the light delivery component. So that's how just to clarify, there's not a separate photoacoustics transducer. It is the main ultrasound transducers with that addition of the fiber jacket.
Mm-hmm. Yeah. Um, we're wondering about, there's a question here kind of wondering about the transducer connector. So we talked about the having the triple transducer connector and being able to switch between transducers live.
Hmm.
There's a question about whether we could use multiple transducers at the same time.
Oh, that's a good one. Unfortunately, no. I mean, you can use them at the same time in the sense that they're all connected, and then by pressing on the system interface, which one you want to be active, that's how you would run it. But no, we can't run them simultaneously. Though there are some ideas with our with our electronics team on how we may make some advancements there in the future to potentially allow something like that. I know. I've actually heard that question before, and so unfortunately we can't do it today, but it's something we're looking at as potentially something that could be possible in the future. I know there's some applications where people may want to be imaging multiple things at the same time.
Mm-hmm. Yeah, that actually leads to another question. You mentioned the future. If you could speak to sort of the future roadmap of the system, there've been a couple of questions about other transducers, other modes. So just sort of a general overview of what the future plans are for this system platform.
Yeah, I think we're looking at our position really today is what, people have asked what other modes might we add, and so I've had that question in general, not just on the call here today. Our position really at this point is we do want to get early systems out into the market, and we want to hear what people have to say. We're also listening to feedback through some of the early demonstrations that we do. So I would say we're more in a listening mode now, where we really want to hear what are the popular things that people are looking for. Obviously, Doppler modes come up as being a candidate. There's a lot of these plane wave. We're doing plane wave acquisition now, but how can we develop further into plane wave imaging modes? So those are kind of the things that we're looking at. We're always looking at ways that the functionality of the interface could be enhanced. So I mentioned that already. Some of the things on the API and the programmability of the system to do more of that online as opposed to offline. Those are things we're looking at. And then longer term, we've got projects. I mentioned the dual frequency transducer. That's something where we see a lot of potential now that we actually have a system that has this full bandwidth, having the ability to combine low and high frequency system transducer into one package and to use that for some applications would be quite interesting. So those are some of the key things we're looking at. But as I say, it's really about listening to our early users as to what direction they may want us to go.
Mm-hmm. Mm-hmm. Great. Yeah, that's great. There's certainly with this platform, it seems to be very open-ended, and there seems to be lots of different directions that we can go. So yeah, there's going to be lots of feedback coming from the market. I'm just sort of parsing through the list of questions here. Just wondering, there's a question that's wondering about on the VADA user interface on the screenshots that you showed, there was obviously some pre-configured transmit delays and pre-configured waveforms. Right. There's just a question wondering about the customizability of those different sections and how deep you can
go. I think it's a good question. It really, I think some of those things come down to the specific, maybe the specific waveform that you are looking for. I would say in general, though, it is quite flexible. I mean, there's ability to, because you can get to the individual elements, because you can get to the timing on a given element arbitrarily. All of that can be set up. So, I guess it's maybe a tough question to answer without maybe a specific example, but that's the kind of thing I think where perhaps that's worth a follow-up discussion and to try to figure out the particular configuration that's being looked at, and we could definitely dig down and see if that's how close to that we can get.
Yeah, that's been my sense for well for any of these kinds of questions is that it's just when you start digging into the VADA user interface and start going really deep into the areas where you can customize and change everything, and then even breaking out and going to the XML and going really deep, it becomes very, very open-ended in the things that you can do. One final question, just wondering if you could speak to the format of the data that comes off the system. A lot of users would be familiar with the format of the CINEs. Some users may be familiar with the format of the RF data that comes from the current 2100 and 3100 platforms, but with this platform, with this ADC data, what format is that data in? How is it on the system? How do you access it? What do you do with it?
Right. So all of the RF mode features that we have on current systems today is supported. So you can get access to the IQ data, the reconstructed the beamformed IQ data, the reconstructed RF form of that same data. We do have the raw format where it gives you the ability just to look at the linear pixel data after envelope detection, and then obviously all the movies, CINEs, images, and things. So that all still stands. When we get into the individual channel data, what you're going to get is a new format, and we have documentation and example scripts for how to read all of that. But it would essentially be a fully sampled RF signal that would come for each individual channel. So you would get, and then for the size of the aperture that you choose. Depending on how you then configure the pulse sequence, you're going to get different. You as the user would have to know what sequence you had sent. So you're reading in essentially a series of frames that are either individual lines or individual lines with then apertures that are varying depending on what you've set. So we don't, again, probably this is back to the earlier question about getting some advanced information and things. These are, manuals and scripts and packages and things that we will be preparing soon as we approach the launch of this product. And those are things that we can certainly share with potential users up front for them to understand how those formats would look like.
Yeah, great. Okay, it's good to know that there's all those different formats and the different possibilities. There's a question here about transducers and transducer availability that I can actually field this one. The specific question is whether or not there's a 1 megahertz transducer already available. There was a slide that talked about the bandwidth of the system from 1 to 71 megahertz. And at this point, the lowest frequency transducer that we have operating is down to 4 megahertz, which is the lower bandwidth of the P10 phased array. It's whether the frequencies of the transducers at the low end will really be dependent on what suite of transducers SonoSite has available for their export system. I cannot remember if there's one that goes lower than 4 megahertz. I'm not sure, Andrew, if you remember that.
I don't recall, but we could check. I think so. And it would be our lower band is 1, so it would be something potentially centered maybe around 2. Maybe have something like a 1 to 3 type of bandwidth.
Yeah.
Running something at 1 megahertz, I wouldn't say it's off the table. It's strictly speaking, right out of the box, the system's probably not going to be set up to do that. But that's if there's a real need for that, that's something we could go back and look at and see if there's any way to potentially push a little lower in frequency. But so again, so kind of right up against the edge of what the system is doing currently, but something we could certainly look at.
Yeah, definitely. Okay, there are a few more questions, but we are sort of getting to the point where we'd like to wrap up. So I think we'll start moving into kind of the wrap up portion for those few questions that we haven't gotten to. We will do our utmost to follow up, and we. As I said, we did record. We are recording this webinar. Andrew, if you could jump to the next slide. Have this webinar recorded. It will be sent out to all of those registrants who did register, whether you attended or not. We will be sending out the recording. And the recording will also be posted on our website, which is a great resource for everything VisualSonics related to current systems and future systems, obviously now talking about the F2. There are web forums on there where you can go ahead and submit questions, whether it's related to technical questions, anything service related, any scientific application support questions that you've got. Please go ahead, use those web forms and submit any questions. We are quite active on social media, so do follow us on Twitter and LinkedIn and Instagram and YouTube. We do like to try to post webinars on our YouTube channel as well. There's a section on our website, of course, for events. We are generally pretty active at conferences. However, obviously at this time right now, not so much. A lot of conferences are being canceled or postponed. But going forward, when things turn the corner, and we will be definitely quite active again at the conferences and society meetings. In terms of other material that you can access online, in addition to our website, we also have our Learning Hub tool, which we've been working on building out a video library for all different aspects of the system: imaging, animal preparation, data management, data analysis, and obviously, again, in this time when so many of us are staying in, working from home, this is a great resource, and we're going to keep working on this and trying to build this out. So I think with that, we will wrap it up. Thank you very much, everyone who attended. We know it's a bit of a crazy time right now in the world, and we very much appreciate you all taking the time to attend and give us your attention. And do stay in touch, and everyone stay safe. Thanks so much.
Great. Thanks, everyone. Bye now.